Hello. Okay, today we'll be talking about more about ripple counters. So let's begin. So binary, I'll give you an example of a 4-bit binary ripple counter. So see that in my previous lecture I have talked about 2-bit binary ripple counter and how it works, how it functions. So in similar manner, this 4-bit binary ripple counter with T flip-flops will work. You can see that it's the same thing. The only addition to it is the new reset button right here. Okay, the reset button is shorted. You can see all the reset button is shorted and it is connected to a reset pin, right? So the thing is happening is for normal operation I'll be putting 1 at here so that my flip-flops won't be getting uh, reset command, or the reset won't be happening. Okay, if I give 1, but if I put instead of 1, if I put 0 at the reset pin, all the active low reset pins will be turned on, and what will happen is whatever my input or clock signal is, it won't matter anymore. The output will reset to 0. It won't change until I change the value of 0 at reset pin to 1. Okay, so for normal operation I'll be putting 1 at the reset pin. Okay, that's the main thing. Okay, so now uh, so this is a 4-bit binary ripple counter. So many times we need a special type of counter known as BCD ripple counter. So 4-bit binary ripple counter should count from 0. So as we are seeing that I have taken negative age triggered flip-flop, so it is basically an up counter. So it will count from 0 to 15, right? But in BCD we know that in uh, in BCD we have 0 to 9. So we need to do that. So how to do that, how to make a BCD ripple counter? Then it is actually very easy to do. See that, let me show you how to do this, a BCD ripple counter from the 4-bit binary ripple counter. So first of all, I need a 4-bit binary ripple counter. So here it is in front of me. So see that I want that it should the 4-bit binary ripple counter uh, should give the state from 0 to 9, right? I need this for BCD ripple counter. Okay, so what I can do is, when the binary ripple counter will generate 1010, or in decimal that is 10 as output, I'm going to reset the whole thing back to 0. That's what I'm going to do. So see that in order to get this signal, this specific signal, so what is happening? So this is my MSB A3, this is A2, this is A1, and this is A0, right? So see that when I'm getting actually 1 at A3 and A1, this is a unique case. Okay, this is the first time, see that in 1010 or decimal 10, 10 A3 and A1 gets A3 and A1 becomes or have the logic value of 1 for the first time. Okay, both are 1 actually. Okay, so I'm going to use that. So what I can do is, see that what I'm doing is, so A3 and A1, I'm going to take the A3 and A1. Okay, and what I'm going to do is, see that I'm just drawing a NAND gate. So when A3 and A1 both will be 1, then I'll be having a 0 at this end, and I'm just connecting this with this reset pin. So interestingly, what will happen when when the counter generates 10, immediately the whole thing will be resetted, whole thing goes to 0. So actually this will happen in a very fast manner that we won't be actually considering, or we won't be actually seeing the 10 coming from this counter. So basically what we'll be seeing is something like this. We'll be seeing that it is counting from 0 to 9 and then going back to 0 again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the reset happens. When it reaches to 10, that immediate moment it will become 0. So the 10 becomes 0. So it is technically a BCD counter right now. So the circuit you're seeing right now is a BCD counter. So this is a BCD counter, BCD ripple counter. Okay, so I think that's that. So another thing I want to talk about is, see that you can also design a ripple counter. So this is a ripple counter. So I have talked about BCD ripple counter right now. So you can also change, I can also change this a bit. So when I put T, when I'm fixing the value of the T flip flops input to be 1, logic 1, it actually is equivalent to something like this. So D flip flop, and this is the toggled output, is equivalent to something like this. So give a thought to it, guys. Give a thought to it. Try to understand why it is, why I'm saying this. Because T is equals to 1 means it is always toggling at the output whenever it reaches, whenever it receives edge. And similar thing is happening at this same connection. Whenever it receives a clock pulse, the output is always toggling. So both the circuits are similar. Okay, now moving on to the next one, that is, so now we understand what is a BCD ripple counter. Okay, so now we understand what is a BCD ripple counter. Okay, so now let's talk about the next thing, that is, so see that the upper circuit can be modified into something like this. So T is equals to 1 is something like this. I have talked about it. So give a thought to it, guys. Try to draw the wave shapes. Okay, so now the 4-bit binary count sequence. So I'm talking about 4-bit binary counter. The counting sequence, I have talked about it, 0 to 15. Okay, right. So it will be going from 0 to 1 to 2, 3, and you know the thing. So let's move on. So that's that. So 15 and then going back to 0 again. So that's that. So BCD ripple counter, I have already drawn the circuit for you. Let's consider for a moment that that BCD ripple counter is a box, something like this. Okay, so what is this thing now? So you can see that I have actually, this is a BCD counter. So it will count from 0 to 9, it will count from 0 to 9, this will count from 0 to 9. So what is happening, I'm giving a clock pulse at this point, the first one. I'm calling it a units digit. This is known as tens digit, is known as hundreds digit. Okay, so now what I'm giving, giving a clock pulse at this, the first one. So what will happen is, try to understand this one. So it will receive, uh, say when it will be 9, it is something like this. Okay, see this one right here. So all the BCD counter, if you see the construction of the BCD counter, I don't need to go back actually, you know it actually. If you see the construction of the BCD ripple counter, that we have used negative edge triggered flip-flops, right? So see that right here, when the value is 9 at the first BCD counter, okay, the Q8, the leftmost bit, that is something in this position, Q8, in this position high. But when another clock is received via this point, when the next clock edge comes, then it gets to 0, it is 0, right? 9 then 0, right? So it goes back to 0. What happens is, it's something like this, it's 0, 1, 0. So what happens is you get a negative edge at Q8, and this serves at a clock pulse for the next BCD counter. That means the reading at this counter will be something like this, and similar thing will happen after 1, then 2, 3, 4, 5, 6, 7, 8, 9, when it will be 9, and then again back to 0. What will happen? It will receive a negative edge, and it will read as 001. So this is known as a 3-decade decimal BCD counter. So you can easily understand it can count till 999, right? Okay, that's all for today. This is the working principle of BCD ripple counter, and what you can do with BCD ripple counter. You can make decade counters, 3 decade, 4 decade, whatever you like. Uh, Try to draw the wave shapes to understand clearly. Thank you guys. If you have any question, please give a comment.